Humanity has now identified over 6,000 exoplanets, plus dozens of local moons sitting right in our own cosmic neighborhood. Space agencies face a severe bottleneck. Budgeting for probes and scheduling time on telescopes like the James Webb is a zero-sum game, forcing scientists to make difficult choices about where to look. We have to distill these thousands of candidates down to the 10 worlds with the absolute highest probability of harboring life. To find them, we have to look past the media hype. In astrobiology, habitable doesn't necessarily mean Earth-like. It refers to a specific chemical balance: liquid water, essential building blocks, and an active energy source. The standard habitable zone metric often identifies thousands of targets while ignoring fatal variables, such as toxic atmospheres or sterilizing stellar radiation. Instead, we can evaluate these planets through the lens of the astrobiology return on investment. This chart filters our 6,000 known candidates through layers of probability. We check for the right temperatures, detectable chemical signatures, and physical accessibility, leaving 10 high-value targets. This framework compares the capital cost of observation against the reliability of the evidence we get back. Identifying a living world requires treating space exploration as a strategic investment portfolio, carefully balancing high-risk data from deep space against the high-cost, high-certainty missions to our own solar system. Group 1 is the local echoes: Mars, Venus, and Ceres. These are our closest neighbors, requiring the least travel time to investigate. Mars represents a straightforward investment. We have the capability to land rovers for direct mechanical sampling and rapid data return. The trade-off is that the Martian surface is heavily irradiated and dry. Our instruments are searching for ancient, extinct microbial life rather than an active biosphere. For Venus, the investment focuses on atmospheric probes. Telescopes recently detected phosphine gas in its clouds, raising the possibility of biology in the cooler upper layers. However, these phosphine signals are heavily contested. The data may actually represent abiotic sulfur dioxide produced by volcanic activity. The dwarf planet Ceres has a water vapor atmosphere, hinting at salty underground oceans, but it lacks the robust tidal heating needed to power a persistent biological ecosystem. These local echoes offer the most accessible data, yet their harsh environments mean scientists are likely chasing microbial ghosts and ambiguous gases. Group 2 includes the remote exoplanets, K2-18b, TRAPPIST-1e, Proxima Centauri b, and LHS-1140b. Investigating these worlds requires an immense hardware investment. We must use our most advanced space telescopes to capture faint starlight passing through their atmospheres. This graph simulates transit spectroscopy for planets like K2-18b. We can detect potential biosignatures, like dimethyl sulfide, or DMS. But spectroscopy only allows us to infer biology. Unknown chemical processes could easily produce these same light dips without life being present. Proxima Centauri b is a high-priority target simply because of its proximity. It is our nearest neighbor at 4.24 light-years away and sits within its star's habitable zone. But the trade-off is its volatile host star. Frequent X-ray and UV flares likely strip away the planet's atmosphere, making surface water retention nearly impossible. Investing in exoplanets generates exciting near-term data, but it leaves us in a state of uncertainty, unable to definitively rule out dead, abiotic chemistry. Group 3 consists of the high-yield ocean moons, Enceladus, Europa, and Titan. This investment requires multi-billion-dollar physical probes designed to investigate the environments underneath thick ice shells. Europa is a primary target because it possesses all 3 mandatory ingredients for life: a subsurface saltwater ocean, essential chemical elements, and an energy source created by tidal heating. For Enceladus, we can fly probes directly through water plumes erupting from the surface, providing direct confirmation of organic compounds and a diverse redox environment. The trade-off is the timeline. These missions require generational patience and massive funding to simply reach Jupiter and Saturn. While the cost is high, these moons offer the only realistic opportunity to plunge a physical instrument into a thriving alien ocean. To make a decision, we map these 10 worlds based on accessibility and evidence reliability. Exoplanets like K2-18b score low on both axes, unreachable with interpretive remote data. But in the top right, Europa, Enceladus, and Titan dominate, returning physically irrefutable data. If you want the dream of a global ocean world like Earth, keep following LHS 1140b and K218b, even as we never reach them. If you want irrefutable proof of alien life in your lifetime, focus exclusively on the local gas giants. The definitive evidence of extraterrestrial life will likely arrive as a tangible chemical sample pulled from the dark, icy depths of our own solar system.